The third method is to solve the differential of the unit step function. Why can we solve the unit impulse response by the differential of the unit step function? Let's make a derivation. For a zero-state circuit, we suppose the response under the excitation of the unit step function is st, and the response under the excitation of the unit impulse function is ht. We know delta t is the differential of epsilon t, and we want to know whether ht is the differential of st. Let's derive it. We still use such a unit pulse function. Similar to the discussion in lecture A2, this unit pulse function can be seen as the sum of two unit step functions. We can easily get pt equals 1 over delta times epsilon t minus delta t. We suppose the response of the unit pulse function pt is hpt. Because the whole system is in zero state, according to the discussion in lecture 51, we know this is a linear system. In other words, the response with the sum of two excitations is the sum of the responses under them respectively. The response with epsilon t is st, and the response with epsilon t minus delta is st minus delta. When they time a coefficient, the corresponding responses should time the same coefficients. The responses can be written as this form and this form. In other words, this is the response of this window function. We've known the limit of the unit pulse function when delta tends to 0 is the unit pulse function delta t. Obviously, the limit of hpt when delta tends to 0 is unit impulse response. So, we get this conclusion by substituting this expression into the conclusion. We can get this. What's this? Isn't it a standard expression of the derivative of s? So ht equals ds over dt. It verified our supposition that if we can solve the unit step response st and its derivative is the unit impulse response ht. Specifically, if we want to solve the unit step response of this circuit, the circuit should be like this. We know IC equals epsilon t. We also know UCT equals UC 0 minus plus 1 over C times the integral of IC from 0 minus to t. The circuit is in zero state, so this part is 0. By substituting this expression into this, we can easily get it equals t over c times epsilon t. The sum of the two parts is st. Now we need to solve ht. Firstly, we solve ht for IC. It equals the derivative of epsilon t, which equals delta t, obviously. Secondly, we solve ht for UC. It equals the derivative of t over c times delta t. You should notice that there are two terms with t, so we need to use a fractional derivative method. Then it can be written as the sum of two parts, 1 over c times epsilon t plus t over c times delta t. This part is just ft times delta t we've discussed before. Do you remember it equals what? It equals f0 times delta t. The f0 here is 0, so this part is 0. Then we know it equals 1 over c times epsilon t. By comparing this result with the one in the previous page, you will find they are the same.